Hi.
Hello and
Hello.
dear students.
Hello.
I am audible and also the board is visible to all of you.
Yes.
Hello.
All of you.
So it's not visible, Kitely.
Which is not visible?
The board, sir, the board.
This board is not visible, is it? Are you able to see this Dayananda Sagar University thing?
Same thing, brother.
Yeah. Can someone else also tell me if you're all able to see or not? Okay. So good morning to all of you. Can someone tell me whether the board is visible or not? I will then start.
Yes.
Okay, fine. If it is visible, then I think I can go on. And also, one thing that I want to tell you beforehand, today we are looking at a very, very big topic of rigid body dynamics. I need to be a little fast in actually telling you all the important ideas, and also we should solve the problems. Okay, so I'll be a little fast today. That's number one. Second one, I think we will allow you to actually unmute yourself for a while. And if you all are very responsible and then use it properly, then we can use it for the entire class. Otherwise, if it becomes actually too much of a nuisance and disturbance for the class, then we may have to take out that say option from you. Is that all right? Is that understanding all right with all of you? That you will be given the responsibility of using the mic very judiciously and responsibly. Is it okay? Can I get some reactions? Prajwal sir, have they been unmuted?
Yes.
Have you? I think you can mute everyone. You can unmute everyone, and then
Okay.
mute where they can actually unmute whenever they want.
Because we don't want them to misuse, that's why.
Correct. But can you make me host? I will take care of it.
Okay. Okay.
Make me host. I'll take care of that. Prajwal, make me host. Okay. I'm allowing you to unmute your mics, okay, with understanding that you will all very judiciously use it. Okay.
Okay, sir.
Can you all respond? Is my board visible to all of you?
Yes.
Yes, sir.
Okay. So today we'll be looking at
Sir, no chat possible.
dynamics. We'll also include system of particles in this itself. For us, one of the most important topics, okay, a lot of questions do come on this particular idea, okay, and if you are especially interested in the NEET examination and the mains, this chapter will be very, very important for you. CET also plenty of questions come. So I'm starting with, first of all, system of particles.
Sir, how many marks carry?
I'm sorry,
How many marks carry?
this particular one. Usually you will get at least 2 to 3 questions in CET. Okay, it can be even more in the case of NEET. In the case of NEET, it can even be 4 marks, 4 questions sometimes.
Excuse me, sir.
Yeah.
Sir, can you write still more darker?
Why this is not visible, is it?
No, sir, it's light. It's looking like light. We cannot see. Can you write still more darker?
Okay, I will do that. Yeah.
Thank you, sir.
Okay. Now in the system of particles, the first idea that we look at is the center of mass. Is this visible?
Yes, sir.
Yes, sir.
Okay, center of mass. Hello? Hello? Rajul, can you switch on your video? The idea of center of mass. Now, the idea of center of mass basically is when you have system of particles spread over at different positions, then we define the center of mass of this particular system, okay, with respect to a particular x and y axis. So now, how is that defined? The center of mass corresponding to the x coordinate will be simply written as mi xi summation of this divided by summation of all the masses. Similarly, YCM will be equal to summation of the product of all the masses with its y coordinate divided by sum of all the masses. And one can also say if the particle is spread over all the 3 dimensions, then you can also define ZCM as this. Mi Zi by summation of all Ms. All Ms. So this is the idea of the center of mass of for a system of particle. Now let us try to understand what will this center of mass be for an extended object. For an extended object, you can say that the center of mass will be essentially integral of dm into x divided by integral of dm. And here, an important point to note is that if you have a uniformly distributed object, then the center of mass will be same as will be same as the geometrical center of the object. Okay. For example, if I have a rod, of length L, then the center of mass will be exactly at the center, which will be at L by 2. This is where the center of mass is going to be for a uniform rod. Okay. Now, for a rectangle, in the same way, join the two diagonals. This will be the center of mass. And it's quite important to note the center of mass of the uniformly distributed objects. Okay. So I'll try to actually give you a list of that here. So I've done it for the case of a rectangular plate or a rod. Let me now give you for a ring. For a ring, the center of mass will be at the center. Okay. So therefore, I would say center of mass need not be within the material medium. It can even be outside. The medium. That's what has happened in this case. Okay, it's outside here. The material is somewhere here, but the center of mass is outside. So that's something to important point to note. Second one, if you consider a semi-ring like this, instead of a ring, let us consider a ring which is of this kind. Now, for this ring of radius r, the center of mass will be present somewhere here. Okay. Now, what is this YCM given to be? So the YCM in this case, the center of mass here will be equal to, for the case of a ring, will be 2r by pi. So this will be for a semi-ring. Where is the center of mass? Will be 2r by pi. Okay. If you all have written down this, let me go to my next page. Have you all written down this?
Yes, sir.
Yes, sir.
Thank you. So now let me go to my next page and then see for a few more things. Now, for the case of a disk, you all understand by a disk, isn't it? Disk is actually a solid one where the material medium is present everywhere inside this. Okay, this is your R, let us say, disk of radius R. Then the center of mass will be at the center itself. Center of mass will be at the center. But for a semi-disk, where do you expect the center of mass to be? The center of mass for a semi-disk is going to be at a distance which is given to be 4r
by pi.
Sorry?
4r by 3 pi.
For a disk will be 4r by 3 pi. 4r by 3 pi for a semi-disk. Okay. Now for the case of a cone, okay, where do you expect the center of mass to be? Okay, it will be again at a point here. If this height is given to be h, any guess as to what YCM is going to be? Is h by 4. So the center of mass therefore will be at a height of h by 4 from the base. Okay. Now what are we going to do with this center of mass? Now center of mass can always be assumed as the point where the entire mass is concentrated. Switch off the mic, someone there is concentrated. Okay. So if you basically have a cone here like this of mass m, then this is equivalent to considering a mass m at a point h by 4 from this point. So these two are equivalent, remember. Okay, you can consider this to be like a point mass present at a distance of h by 4 from the center. Of course, it should be along this axis. Along the axis, you should keep it. So if you keep the entire mass here, it's equivalent. That's what the idea is. Now, where can I use this? Where can I use this? So if you want to find out, for example, potential energy of an extended object, Now, how do you do that? You'll say that you have a rod which is standing here on the ground here in this way of mass m. Now, if you want to find out what is the potential energy of this, then the potential energy will be equal to the total mass which is concentrated at the center of mass. Okay, what is the height of the center of mass? YCM.
Audible,
The
sir.
potential energy will be equal to simply mg into YCM. So that's a big advantage that you will have when you want to calculate the potential energy. Okay, if you know center of mass, it's always easier to calculate this energy. Now, this is an obvious question which I wanted to come to. That's good that you're asking me in the chat box. Third one. Now, what is the meaning of center of gravity? Is it different from the center of mass? Okay. In fact, center of gravity is same as center of mass if acceleration due to gravity is constant over the entire object. All right. Now, what does that mean? It means that if you actually have a rod or something here like this, then if you consider what is the force experienced by the small part here, dm, let us say, then this will be dm into g. Okay, dm1 maybe I'll call it as. Another point here, dm2. Okay, here also the force will be equal to dm into g. If the g were to vary from one point to another, then the center of gravity will be different from center of mass. But if g is constant, then this is the point where you have center of mass and also center of gravity. Center of gravity, let me call it as Cg. All right, Cg. Center of mass, I'll call it as Cm. So when will both of them be same? If the g is basically uniform over the entire rod. Roughly, g is constant due to the earth over a large area and also large heights. Up to something like 100 kilometers, you don't have to worry. G will remain almost the same value. And as a result, you'll find that the center of gravity and center of mass both will coincide. Okay, I think I have answered this question on the center of gravity. Okay, fine. So with this, let me now move on to having done the center of mass idea. Let me move on to another idea in the center of mass itself. Can I go on?
Yes, sir.
Yes, sir.
Now, the second point that I want to look at in the idea of the center of mass is of the system of particles. Let us say that I have many particles here, and each particle having mass m1 has a velocity v1, and this actually has a velocity v2, and the other one will have a velocity v3 and mass is m3. And this is now going to move with velocity v4 and mass is m4. Then the obvious question is, what is the velocity of center of mass? Velocity of center of mass. The velocity of center of mass will be equal to, again, summation of all the masses with this velocity divided by summation of the masses. This gives me the velocity of the center of mass. Similarly, I can also define acceleration of the center of mass. Acceleration of the center of mass. That will be equal to summation of mi. So multiply all the acceleration with the mass divided by the total mass should give you the acceleration of the center of mass. Okay. So this is another way of essentially calculating the center of mass. I mean the center of mass idea. Now, if you have acceleration, I should also talk about the force experienced by it. If the force experienced by the system of particle will then be given by F is equal to whatever the total mass of the object, summation of mi, all the masses, into ACM, or can be written as simply mass of the system into ACM. This gives you the force experienced by the system of particle. Okay. Now, as a note, take this up. For two particle system, M1, M2. Now let us say that this is getting attracted towards M2, M2 is getting attracted towards M1. So there's a force F1 here and a force F2 here. Because of which this will start accelerating with A1, this will start accelerating with A2. Then what will be the acceleration of the center of mass for this two particle system? It will be equal to M1A1 plus M2A2 divided by M1 plus M2. But look at it, F1 and F2 essentially are the mutual attraction between the particles, and therefore I can say that F2 should be equal to minus F1. Now what does that imply? It implies that now ACM will be equal to F1 minus F1 divided by M1 plus M2, and that will be equal to 0. So when you actually have two bodies attracted because of their own mutual attraction, okay, then these two forces will be in fact called as the internal force. Acceleration of the center of mass will be 0. So I make a very important point here. When only internal force act, only internal forces act, then acceleration of the center of mass will be equal to 0. It will not have any acceleration for center of mass. That's a very important idea to have. Okay. Now, when the only internal forces are acting, you can also show that M1 V1 will be equal to M2 V2. This also is can be proved. I'm not going to prove it, but I'm going to just give you as a result. All right. That also implies that when only internal forces are acting, then M1 delta x1 will be equal to M2 delta x2. Okay, this also will be a valid expression where delta x1 and delta x2 are the displacements of the body. All right. So I think some of the important points I wanted to note I have done it here. Can I go to my next problem? Next page rather. If you all have written down this, can I go to the next page?
Yes.
Okay. Fine. So the next idea that I want to basically look at is the moment of inertia. For the case of number one, system of particles. Moment of inertia is generally defined as summation of mi ri square. Okay, that is, if you actually have an axis of rotation here about which you have different masses considered m1, M2, M3, M4. Now each of them basically has a perpendicular distance R1 given here like this, in this way. Then the moment of inertia will be given by summation of this in this form. Now, for the case of an extended object, I'm considering an object now. Moment of inertia will be given as integral dm into r square. Summation will be replaced with integral. M will become dm. Then ri will become r square, where r is continuously varying from one end to the other end. Now, if you use this idea, you'll be able to find out the moment of inertia of different objects. Okay, about the axis, which I call it as the passing through center of mass. So what we'll do is we'll try to actually look at what is the moment of inertia of the different objects about an axis passing through center of mass. Okay. Now the first object, let's consider it to be a rod. For a rod of length L, then it is basically about an axis passing through the center of mass. Then the moment of inertia will be written as mL square by 12. Okay, this is the moment of inertia. Of the rod about the center of mass. Secondly, if you want to now find out what is the moment of inertia of a plate, of width A and length B, about the center of mass here, the moment of inertia will be written as m A square plus B square by 12. Okay. Now, for a square plate, this would be very interesting. No? For a square plate, where I can take A and B to be same, then the moment of inertia will be equal to m A square by 6. M A square by 6. This is about the center of mass. This is for the case of a plate. Now, let's do it for other things as well. Now, for the case of a ring, all right. The moment of inertia about the center of mass will be simply mr square. Mass is m, all right, for all of them. Fourth one, for the case of a disk, the moment of inertia is given to be mr square by 2. Everything is for center of mass until now. Okay, we have not done anything else other than that. Next one will be that of shell. Shell essentially means that it actually has certain thickness, but most of the inside is hollow. Okay, that's called as a shell. Okay, shell is essentially this of radius r. Its thickness, in fact, is very small when compared to its radius. So I don't have to worry about the thickness. For a shell of that kind, about the center of mass, you'll find that this will be given as 2 by 3 mr square. 2 by 3 mr square. And for the case of a solid sphere means it's like a shell, but it's completely filled inside. Okay, more like the rave unde or the laddu. Okay, so you'll find that this solid sphere will actually have or like a cricket ball. Okay, it's going to be like the moment of inertia will be equal to 2 by 5 mr square. 2 by 5 mr square. 2 by 5 mr square. Okay. Now finally, for the cylinder, if you have a cylinder here of length L and radius r, and if it is rotating in this way, then moment of inertia will be equal to mr square by 2 if it is a solid cylinder. If it is a solid cylinder, then if it is a hollow cylinder, if it is a hollow cylinder, then moment of inertia will be equal to mr square. I think this table is important. You should really remember these values. Many questions come on the determination of moment of inertia. That is the reason why I'm basically concentrating on this part. Now, in the case of moment of inertia, we actually have what is called parallel axis theorem and perpendicular axis theorem. Now let me tell you both of them mathematically. That becomes easy for you to understand. If I, for example, have a rod here like this, if you know what is the moment of inertia about the center of mass, this is important. You should know the moment of inertia about the center of mass. Then the moment of inertia about another axis parallel to it. Let me call this as IA. So this IA will be given as I naught plus whatever is the mass of this and the separation between the two. Let me call this as D. So plus md square. Mass of this whole thing into the separation between the two parallel axes. So I naught plus md square will be IA. So it's quite easy to find out what will be the moment of inertia there. Now there's one more thing called perpendicular axis theorem. Now what is this perpendicular axis theorem? Tell me about. Let me take an example and then give you the mathematical form of it. If I have a plate, okay, a rectangular plate like what I took other way now. Now this plate, basically the moment of inertia is known about the center of mass here. I know about this. Now if I want to find out what is the moment of inertia about the other two axes, let me call this as Ix and this as Iy. What I know is I naught. Then you can say that Iy plus Ix should be equal to I naught. That is what the perpendicular axis theorem is all about. So you have parallel axis theorem and perpendicular axis theorem given here. Now once you know this, you can start filling up. Can I move on?
Sir, explain once again.
Okay. Now the perpendicular axis theorem basically says, if you know what is the moment of inertia about the perpendicular to the plane. So this is the plane of the plate.
So what is
I know
statement?
what is the moment of inertia about an axis which is perpendicular to the plate. So this is perpendicular to the plate. Axis perpendicular to the plate. I know what I naught is. Now this Ix is the moment of inertia about an axis which is passing through the length, okay, but about the center of mass. This is again another axis here about the center of mass passing here like this. I'll call this as Iy. Then I can say Iy plus Ix is equal to I naught. That's a theorem and it can be proved, but I am not going into the proof of it. You should know the result. That should be good enough for you. So it should be equal to this. Okay. Now I told you that a lot of questions come from this moment of inertia chapter, moment of inertia part. And hence, I would like to spend a little time in using this theorem for some of the objects that we have already done and fill up this table. What we have done in this table is we have obtained the moment of inertia about the center of mass. Let us try to obtain for the other axes now. Okay, I'll say about an axis through something else. We'll find out that. For example, for the rod, let us ask a question. What will be the moment of inertia about one of its end? Not from the center, one of its end. I know what is the moment of inertia of the rod about this. This will be ml square by 12, isn't it? Now, what is the separation between these two? D here will be equal to L by 2 because this is the center, this is the other end. So if I call this as IA, then IA can be written as I naught plus mass into D square. So what is I naught? I naught is ml square by 12, and this will be m L by 2 the whole square, because d is given to be L by 2. So simplify this. ml square into 1 by 12 plus 1 by 4. How much will that be? 12 is the LCM, isn't it? So 3 plus 1, 4. So you get this to be therefore ml square by 3. So I get therefore the moment of inertia of this rod to be ml square by 3. So I filled up in this part. All right. So about one of the end is ml square by 3. I can do it for anything now. All right. For the case of a ring, let us do with perpendicular axis here. Now for the ring, I want to do is find out what will be the moment of inertia about the diameter. So IA is about the diameter. Look, I know what is the moment of inertia about this point, I naught is known to be. That's what is given to you here, isn't it? About the center of mass, and that I naught is given. So what I'll do is, if you want about the diameter, I'll say take one more diameter perpendicular to it. So call this as IA dash. Now, according to the perpendicular axis theorem, IA plus IA dash should be equal to I naught. But look at this, because of the symmetry of the problem, IA and IA dash are the same. They both are same. And therefore, I can write this as 2 times IA is equal to I naught. So what is IA equal to, therefore, will be I naught by 2. For a ring, it is mr square, and therefore, about the diameter, the moment of inertia should be mr square by 2. So about this diameter, moment of inertia will be mr square by 2. mr square by 2 for the case of the ring. All right. Now, similarly, I can find it out for any other thing. Any other thing can be obtained using this idea. Now, if you also do it for the case of a disk, for the disk, I will get again this to be 2IA is equal to mr square by 2, because the moment of inertia here I naught itself is mr square by 2. So what will IA be then? IA will be equal to mr square by 4. So for the case of a disk, about the diameter, what is the moment of inertia given by mr square by 4? So I can go on and basically keep actually working out and then do this. If you are all done with this, I'll go to my next page, because I want to give you 1 or 2 notes on this part.
Yes, sir.
Okay.
So last one is disk, sir.
Last one is disk. Yeah.
Okay.
What I'll do is, in the note, I'll consider a special case of a cylinder, because this question was there in CET 3 years back. Okay, a cylinder, and also in the mains examination. You are asked to find out what is the moment of inertia of a cylinder about an axis like this. See, we generally know what is the moment of inertia about this particular axis, but we never try to understand what will be the moment of inertia about an axis like this, perpendicular to this. Let this be a cylinder of radius r and length L. The moment of inertia of this will be given as ml square by 12, like a rod, plus mr square by 4, like a diameter of this disk. So both put together will be the moment of inertia of this cylinder. Now, similarly, you have a special case like this. You have a rod, but what I do with the rod is I will make it rotate about an axis like this. So it's going to spin in this way. By making an angle theta. This angle, let us call it as theta. Then the moment of inertia of this will be ml square sine square theta divided by 12. Very, very important result. I have actually seen questions of this kind coming in neat. Okay, if the rod is rotated at an angle theta, then the moment of inertia should be given by this. Lastly, what will be the moment of inertia of a cone? If I make a cone rotate about its own axis here like this, in this way, then what will be the moment of inertia of a cone? This will be given by 3/5 mr square. Very interesting, isn't it? 3/5 mr square. So moment of inertia therefore comes in different varieties, and we have looked at it. Are you all okay? Can I go to my next page?
Yes, sir.
Okay.
1 minute, sir.
This is for a cone, all right? This is a rod.
Sir, could you move up? Thank you, sir.
The first case basically is about the cylinder. Switch off the mic. Okay. So if you all are done with this, let me now move on to my next page. Now I think we should look at the idea of torque. Torque is essentially defined as R cross F, or torque per se will be FR sine theta. I think I should take an example and illustrate this idea. Let's say that I have a rod here and this is fixed at 1 end. I apply a force F like this. And now this is the distance R. Now this distance R here will make an angle theta with respect to F. Then what the torque is actually telling us is that with the torque will be equal to R cross F, R into F. So that will be, if the angle that it makes here is given to be theta, then this turns out to be R F sine theta. Now F sine theta essentially is this. This will be F cos theta. So the torque can be understood therefore as R into the perpendicular component of the force. Okay, so this will be the perpendicular component of the force into R will always give you torque. All right. So this is the way that we understand or calculate how the torque is. Now, few important things to note. If you actually have a rod rotating in that way, torque will always be along the axis of rotation. What is the, where do you search for the torque? Should always be along the axis of rotation. All right. Now, if it is making the body move in the anti-clockwise direction, then the torque is taken to be positive. If it is in the clockwise direction, then the torque is considered to be negative. So this way, I'll be having the torque acting on the body. What will torque generally do is torque will make the body rotate. So I can therefore say torque should be proportional to, or rather, if I apply a torque on a body, then the body will start having angular acceleration. Angular acceleration. Then you can show that tau will be equal to I alpha, where I is the moment of inertia, alpha I just told you, tau is tau. This is the second law of Newton. Second law of Newton in rotation. In rotation. All right, this is similar to F is equal to m into a. The same, the equivalent of that in the rotation is tau is equal to I alpha. Tau is equal to I alpha. Another point to note here is that if tau equals 0, then it is said to be under rotational equilibrium. Rotational equilibrium. If F is equal to 0, then the body is said to be in translational equilibrium. If both are 0, then the body is said to be in what is called static equilibrium. Static equilibrium. So what is the condition for the static equilibrium? Both of them must be equal to 0. Please look at it. It's a very important point, and we'll be using this in solving problems later on. Okay, this is the idea of the torque and the equilibrium that comes because of this. Can I go to my next point if you all are okay with this?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. I'm sorry, I'm basically muting everyone and not allowing anyone to unmute now. That is because someone is actually creating that background noise all the time. So therefore, I have to really do this. The only way that you can now converse with me is through the chat. Okay. So now basically I have looked at the idea of the torque and also the Newton's second law. I would like to actually give you some important points on the torque, especially when the bodies are moving. So let us consider one or two examples where I want to illustrate this point to you. Let's say that I have a system like this, where a disk is fixed to a wall, and then I take a string, wrap it around it, and then I have a mass here attached to it. Let the mass of this disk be equal to m and the radius be equal to r. Now what happens if I leave my hand is, this mass is going to come down with acceleration a, and this disk will now start rotating with an angular acceleration alpha. Okay, that is because as the mass moves down, it's going to pull this string down. It will have a tension T, and that tension is going to make this disk actually rotate. Now, if you say that there is no slip anywhere in the system, then you have to find A and alpha. Now, important point to notice, when you say that there is no slip, then it will always imply that A will be equal to R alpha. This is called as a no slip condition. Okay, most of the problems you can assume that A will be equal to R alpha. A is that of this body, alpha is for the disk, but they both are related in this way. A is equal to R alpha. It's always a known thing. Now, let us actually use the shortcut method for finding the acceleration. Acceleration will be equal to the external force divided by the net mass or the total mass. That will be equal to, the external force here is only mg. There is no other force which is going to actually make this body move, mg, divided by, there is mass of this object plus This body is also rotating. Whenever it rotates, there is an effective mass that you need to consider. The effective mass of the disk will be written as m equals I by r square. This is called as the effective mass. So this will now become I by r square. So how do we calculate the acceleration of a system like this? Should be simply mg by m plus I by r square, where I is the moment of inertia. This is the shortcut method. Don't ask me how I derived it, but I'm giving you the shortcut method which basically works. Okay, so I can find out A. Once I find A, then alpha is easy to find because it's simply A by R. So this will then turn out to be mg by R into m plus I by R square. So I get the expression for alpha, I get the expression for A, both in fact in this way. So this is a shortcut method for finding it out. Okay. Now I would like to go to my next page if you all have done with this. Can I go to my next page? Okay, well, once again, I'm trying to allow you to unmute so that you can interact with me if you have any doubts and other things, okay?
Okay.
I'm going to my next page. Can I? Any doubts? Any problems?
Could you explain once again, sir, the previous one?
Oh, okay. Now, I have basically a disk attached to a wall here like this, and I have a string which is wrapped around it, okay? And then the string basically will go along like this, and then the free end is connected to a body of mass m. Now, if I allow this mass to come down, this will come down with acceleration a. This will start rotating with angular acceleration alpha. I have to find what this a and alphas are. I'll always say that use this condition called no slip condition, where a will be equal to r alpha. Then I told you how to calculate acceleration using a shortcut method, like what we had done in Newton's laws of motion. Similarly, can I find out what is the external force? External force here is mg, okay, divided by the total mass. The mass of the block plus the effective mass of the disk. What is the effective mass of the disk given by moment of inertia divided by r square will be the effective mass. So if it is a disk, then the effective mass essentially will be equal to m r square by 2 into r square divided by r square. So this will become m by 2. So what is the effective mass of a disk will be m by 2. So that I am in general writing is as I by r square. So use this one, then you'll be able to get the acceleration very, very quickly. Once you find a, alpha can be obtained as a by r. So I just wrote it down like this. Is it okay? Can I go to my next page?
Yes, sir.
Yes, sir. Thank you, sir.
Yes, sir.
Thank you. The next idea in the case of rigid body dynamics is about rolling. Now, rolling is a case where it has both the translatory motion and the rotatory motion. Both are there. So bodies which can basically roll are the ring, the disc, cylinder, shell, and sphere. These are the only things which can basically roll. Now here, what will happen is the center of mass will be moving with some velocity v, acceleration a. Now it will also have a rotation where the angular velocity is omega and the angular acceleration is alpha. Then you find that the velocities at different points will be different. For example, if you consider this point here, the velocity will be v because of translatory motion, r omega because of the rotatory motion, and that will be in this direction. R omega will be like this, and therefore VA will be equal to V minus R omega. If you consider the topmost point, it will now have a velocity V and also will have R omega in the same direction. So at point B, the velocity will be given by V plus R omega. So V is V minus R omega, VB is V plus R omega. So different points here will have different velocity. For example, here VC will be, this will be R omega. So the velocity will be a resultant of this. So VC will be equal to root of V square plus R square omega square. So in the rolling motion, this is what is important. Every point will have different velocities. What is it, Sanjana? You have some issues? Okay. The no slip condition, I'll also be talking about that now. I'll explain once again here. You're asking me about this no slip. I'll basically look at it. Okay. So I have this point A. Now concentrate on point A. This point A is, which is basically lying on this surface, isn't it? It's rolling on this surface. Point A is called the contact point. It's called contact point. Now at the contact point VA, you have the velocity to be equal to V minus R omega. We say that the body will have pure rolling without slipping on the surface. I should say without slipping on the surface. If VA is equal to 0, this point should appear to be like a static point. Then the friction also will be static, and then there is no slipping possible. Or in other words, V should be equal to R omega. Now V is equal to R omega. In terms of acceleration, what will that be? This V will now become A, omega will now become alpha, and therefore A is equal to R alpha. So this condition of saying V is equal to R omega, A is equal to R alpha is called no slip condition. No slip condition. Under the no slip condition, there will be pure rolling of the body. The body will have pure rolling during this time. Okay, and that is your idea of no slip condition. Someone asked me about it. I hope I have explained that again. The same thing is happening also in my previous example. Okay. Can I go to my next point here? Here itself, I need to actually add few important points to note. When the body is rolling on a surface like this, okay, if it's rolling with a uniform velocity V and omega like this, where V is the constant and omega is a constant, and we'll have V is equal to R omega, then you can be sure that the friction here will be 0. Friction for this point will be 0. There's no friction at all there. Second point. If you actually have a body here like this, then if I apply a force here F such that there will be an acceleration A and an angular acceleration alpha, then the friction at this point, F, will be given as, this is for pure rolling only, okay? Friction for the case of pure rolling can be written as, capital F into mr square minus I divided by mr square plus I. This will be the friction. Now the question is, what kind of friction is this? This friction here will be called as the static friction. All right. Whenever body actually has pure rolling, then it is not skidding. Okay, then the friction has to be always static in nature, and that expression is given by this idea. If you are okay, I would like to go to my next page to tell you another important point about rolling. Is it okay? Can I go on? Can I go to my next point?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay. This is about rolling on an inclined plane. On an inclined plane. So the body is rolling here like this on a plane. There should be some amount of friction, otherwise body cannot roll. Body cannot roll. Now it starts actually rolling with an acceleration A and an angular acceleration alpha. Mass is m, moment of inertia is I, this body. Then obviously, for the case of pure rolling, that is, it's rolling with A is equal to R alpha being satisfied, even here. Okay, Madan, can you switch off your video? R A is equal to R alpha. Then you can show that A will be given as mg sine theta divided by m plus I by r square. This is also like your shortcut for calculating the acceleration, isn't it? The net force is mg sine theta divided by the total mass. Mass will be one corresponding to the translatory, the other one will corresponding to the rotatory. So m plus I by r square. So therefore, you will find for a first time the acceleration will depend on the kind of body that you have chosen. For example, if it is a ring, then the moment of inertia is given to be mr square, and therefore acceleration will turn out to be mg sine theta divided by m plus mr square by r square, and that will turn out to be equal to half g sine theta. So if the ring is rolling down, then look at it, it will be half g sine theta. If the disk is rolling, you can also say cylinder. They both in fact will have the same moment of inertia. Then it will be moment of inertia is mr square by 2. Then what will happen to acceleration as a result? Mg sine theta divided by m plus mr square by 2r square. So this will cancel off. So half m plus m will be 3 by 2m. So this becomes 2g by 3, 2g sine theta by 3. Okay, so this acceleration will be different. Now, if it is actually a shell, then the moment of inertia is given by 2 by 3 mr square. Then look what happens to acceleration. This will become mg sine theta by m plus 2 by 3 mr square by r square. So this becomes 3 plus 2, 5. So 3 by 5 g sine theta. So you can actually do it for any other object in this way. Acceleration is going to be different. So each one will come down with different acceleration. Please make a note of this, an important idea, and you should have a ready reckoner for this, a ready table for this particular part. Okay.
Sir, can you show the slide properly?
Which
slide?
part?
This slide itself. This slide.
For the case of a shell, moment of inertia is 2 by 3 mr square. So A will be mg sine theta divided by m plus I am going to write as 2 by 3 mr square by r square is already there. So that r square will cancel off 2 by 3 m. Now simplify this. M will cancel off with this m. So 3 plus 2 is 5. 3 goes up. So 3 by 5 g sine theta is what the acceleration is. For a shell, acceleration is given by 3 by 5 g sine theta. Okay. Yeah, good. So my next question basically will be, what will be the energy? So for this, I have to now understand how to calculate the kinetic energy in case of a rolling body. in case of a rolling body. Now, in case of a rolling body, kinetic energy will be given as half mv square plus half I omega square. One is coming because of translated motion, the other one is coming because of the rotatory motion. So it's going to be half mv square plus half I omega square. So this will be the total kinetic energy of the system. Now, if you consider a body which is rolling down an inclined plane, again, this is going to be very important for your CET part. They keep asking you about this. A body which is rolling down an inclined plane like this, it will have a velocity when it comes down here. When it comes down here, it will have a velocity v and angular acceleration omega. Now, if it is coming down by a height h, you can show that mgh will be equal to half mv square plus half I omega square. This will be the expression here given to me. Now, there are two parts here. This is the kinetic energy that comes because of translation. This is the kinetic energy that comes purely because of rotation. So one has to actually find out individually what each one of them is. Okay, this is going to be an important idea, and you should also look at this carefully. So you can say that mgh will be equal to, if I want to find out first of all this, so I'll write as half mv square plus half I omega, I will write it as v square by r square. So I can write this as therefore half mv square into 1 plus I by mr square. And therefore the kinetic energy corresponding to the translatory motion will be equal to mgh divided by 1 plus I by mr square. This will be a very useful relation, and they keep asking you about this. What is the kinetic energy corresponding only to the translatory part? Then it will be mgh divided by this. Similarly, I can also write down kinetic energy corresponding to the rotatory part, that is half I omega square, can be written as mgh divided by mr square by I plus 1. This is how I can obtain the relation for the rotatory part. This is for the translatory part, translatory kinetic energy, and this is the rotatory kinetic energy. And the question generally asked that what is the ratio between the translatory kinetic energy to that of the rotatory kinetic energy? And that will now be written as, if you just write down this, you'll get this to be mr square by I plus 1 by 1 plus I by mr square. This is how you can obtain the ratio between the translatory to rotatory kinetic energy. This will be an important point which will be asked in most of the problems. Okay, I'm left with one more idea, and after that we can start solving questions. Okay, what is that idea about? I'll go to my next page if you all are okay with this.
Yes, sir.
Sir.
The next part is, sorry, I think I just need one more page, then we'll go to the next part. Chaitra, can you please switch off your video? It's going to unnecessarily take the data of all the people.
Sir, please show previous slide.
Sir, the translatory slide, please.
Yes. Once you are done, please let me know.
Okay, sir. Thank you. Done.
Okay. Now the last part here is about the angular momentum and conservation of angular momentum. Okay. Now the idea of the angular momentum comes from the Newton's second law. tau is written as dl by dt. Okay, where this L is called as the angular momentum. Now, how is this angular momentum defined as? Angular momentum, in fact, is defined as m into r cross v, or simply will be equal to r cross, I think I made a mistake, r cross mv. Yeah, this also is fine. R cross mv will be equal to r cross mv. You all know what mv is. Mv is essentially the linear momentum. Therefore, L can be written as Rm r cross p, r cross p, r cross p. So what is the other relation that I have? This is one relation, right? The other relation that I just told you, tau is equal to dl by dt. dl by dt. This also is an important relation. Now dl can be written as tau dt, all right? Or delta L, or the change in the momentum, angular momentum, can be written as integral tau dt. This integral tau dt is called angular impulse. This in fact is the change in angular momentum. Now this whole theorem of saying that the change in angular momentum is equal to angular impulse is called as angular momentum impulse theorem. That will be useful for your problem solving in many cases. Okay, so this is one thing that I wanted to tell you. Next is, if the torque acting on the body, if the torque on the body is zero, then what it means is delta L will be zero, or in other words, the final momentum will be equal to the initial angular momentum. This statement is called conservation of angular momentum. Okay. Now, as a note, write down these 2 points. For a point object, moment of inertia will be written as mvr. That is, if there's a mass here m moving with velocity v like this, with respect to an axis at a distance r, the angular momentum can be written as mvr. For a rotating body, angular momentum will be equal to moment of inertia into the angular velocity. This is for the rotating body. For a body which is rolling, moment of inertia will be made up of 2 parts. One is the moment of inertia that comes because of the rotation, plus the moment of inertia that comes because of translation. So L will be equal to I omega plus mv r. Take it with appropriate signs and then add them up. So this is how you find it for the case of rolling. So I have looked at all the cases of rigid body dynamics in a very, very short duration of time. This is definitely not enough, but what to do, because we have very little time left for all this, so I have to really rush through this part. Okay, now let us look at the problems and start solving one by one. All right, let me go to problem number 1. Okay, fine. So let's start doing it. Find the constant torque required so that a coil of mass 10 grams, radius 1 centimeter, makes at 10 revolution per second in 5 seconds, starting from rest, about the tangential axis in this plane. Very, very nice question, a loaded question. A lot of things needs to be done here. Okay, you have to find out what torque is. For torque, you need two things. One is you need I, the other one is alpha. So let us see if alpha is given to be in this problem. Alpha is given because it says it basically makes 10 revolution per second in 5 seconds. So therefore, it is 10, okay, divided by 5, and this will be multiplied with 2 pi, because then for one rotation I have 2 pi radian. So this is how I should be able to get this. So what will alpha be therefore equal to? Alpha will be equal to so 2 pi into 10 divided by 5. So 5 ones are 5 twos are. This will be 4 pi. Alpha is going to be 4 pi. Plus, what is moment of inertia for the coin is like a disc, isn't it? It's a disc. I have to find out what is the moment of inertia about this point. For that, I need to use the parallel axis theorem carefully. About this diameter, I know that the moment of inertia is given to be mr square by 2. And therefore, I will be equal to mr square by 2 plus mr square. Very, very important. You have to use parallel axis theorem to find out this. So this will be equal to 3 by 2 mr square. Now let's see what this will be equal to. 3 by 2, mass is given to be 10 grams. Okay, 10 into 10 to the power minus 3 into r square. R is 1 centimeter square. So 1 10 to the power minus 2 the whole square. The whole square. So now if I put all of them together, I should be able to find out what the torque is. Now torque will be I into alpha. I will be 3 by 2 into 10 grams. So 10 to the power minus 3, that becomes 10 to the power minus 2 into 10 to the power minus 2 the whole square, that becomes 10 to the power minus 4 into alpha. Alpha is 4 pi. Alpha is 4 pi. I think I have already the answers. Yes. Okay. Let's see if that is the answer that you all are also telling me. So this is going to be 6. What will this be? 6 pi into 10 to the power minus 6. Isn't it? So what should be the answer to this? 6 into 10 to the power minus 6 pi.
How to find alpha?
I'm sorry?
How to find alpha? Can you explain 1 second, sir?
Yeah. Alpha is delta omega by delta t, isn't it? Omega, it is going to make 10 revolutions per second in 5 seconds. So therefore, omega is 10. But in how much time is it acquiring this omega? In 5 seconds. So it should be this. But 10 revolution means what? 10 into 2 pi. Am I right? 10 into 2 pi. I should not miss on that. I should not miss on that. And therefore, I get the answer to be equal to, this will be 10 pi by 2, which is going to be 4 pi. Into 4 pi. So I think there's a little problem with the power, isn't it? 10 grams have taken it all right, 10 to the power minus 2. This becomes 10 to the power minus 4. And then there is nothing else that actually basically takes away the power. So it should be into 10 to the power minus 6. I'll make this as 10 to the power minus 6 and say that the first one should be the right answer for this question. Okay, so I got the first one.
In the diagram they have given m is equal to 10 kg, but the question they have given 10 grams.
That may be one issue, all right? So I'll go with the problem. I will not take this 10 kg. I'll say this 10 grams. Okay, that should be 10 grams. So therefore it becomes 10 to the power minus 6. Had it been 10 kg, then the answer would have been very different. Okay, then I would have got 10 to the power minus 4. Then I would have got 10 to the power minus 4. You're right. Okay, isn't it? Yeah, that is the issue here.
Yes, sir.
Yeah, that is the issue here. Fine. So that's okay. We will slightly alter that. The method is known. That's good enough for us. Second one. A 10 kg boy is standing on 40 kg flat boat so that he is 20 meters from the shore. He walks 8 meters on the boat towards the shore and stops. Assuming zero friction between the boat and water, how far is he from the shore now? Okay. The thing is, this is a problem where you should use the idea of the center of mass. So here is a boat, okay, and the boy is actually standing. A boy of 10 kg is standing on 40 kg boat so that he is 20 meters from the shore. He walks 8 meters on the boat towards the shore. So he's basically somewhere here and he's going to move towards the shore. But initially he's at a distance of 20 meters. 20 meters. Now what happens is, as the man moves, the boat also will move like this. Okay. Now you should know how much the man has moved. Then you will know the new distance. Okay. So whenever you have a problem like this, analyze it in the following way. Okay. So mass is here. Man is standing at some point. Mass is standing at some point.
Sir.
Is standing somewhere here. Now, both of them basically are at a at some point here. All right, some point here. If he walks 8 meters on the boat towards the shore, so he's going to basically walk for 8 meters. All right. So, what is the actual distance that he has actually moved? Because as he move 8 meters here, boat also will start moving like this. So essentially, he would be actually moving for a lesser distance. So the 8 meter is essentially this part, 8 meter. So actually, he moves only a distance x here. Now, how do I find out this? Now, if this is the center of mass, you can say that m into x will be equal to m into 8 minus x. Because center of mass will not move. Both of them will come towards this. So the total distance that he has moved is 8. So boat would have moved a certain distance here. Man would have only moved effectively up to x. So what is this x equal to? Look at this. Mx plus capital M into x is equal to m into 8. So x therefore will be equal to m into 8 divided by m plus m. M plus m. Let's find out that. Mass of the boat is 40 into 8 divided by 10 plus 40. That's going to be 50. So x therefore will be equal to 32 by 5. 32 by 5. What is 32 by 5? What is 32 by 5? 6 point something, right? 6.4. 6.4. Is that correct? 6.4. And now he has therefore moved only by 6.4. So how close is he from the shore? From the shore, he is at a distance of 20 minus 6.4. 20 minus 6.4 will be 13.6 meter. 13.6 meter. And therefore, the answer to this should be first one. Answer to should be first one. I hope I made that point also clear to all of you. This is a problem where I have to use the idea of center of mass because all the forces are internal and hence the center of mass should not move at all. For a system to be in equilibrium, the torque on it must balance. This is true only if the torques are taken about. Now, about the center of mass system, it should be any point on the system. The answer should be any point. So torque should be 0 about any point on this rod, not just about 1 point or 2 points. It should be about all the points. The torque should be 0. Only then the body is said to be in equilibrium. So it should be true for any point on the rod. Any point on the rod. It's not B. It's for any point on the rod. on the system basically should be 0. The third one is a more appropriate one. It's not just only for the center of mass, mind you. It can be for any point here. Okay, that's an important thing to note. Now, let's go to the next set of problems. Fourth one. Which of the following has the highest moment of inertia when each of them has the same mass and same radius? Nice question. Okay. For a ring, what is the moment of inertia given by? About the diameter is mr square by 2, isn't it? For a disk, about its diameter, about any of the diameter will be mr square by 4. Hollow sphere, about any of its diameter will be 2 by 3 mr square. Solid sphere, about any of the diameter is 2 by 5 mr square. Now, if you want to compare, the easiest would be this. For the ring, moment of inertia is 0.5 mr square, right? For the ring, it is 0.5 mr square. For the disk, it is 0.25 mr square because mr square by 4 for the disk. For the hollow sphere, 2 by 3 will be 0.66 mr square will be for the case of a shell, hollow sphere. And then what is the last one given by? This is going to be 0.4 mr square. What is the question? Highest moment of inertia when the body, each of them. So which one is actually the case? 0.66 mr square. So the hollow sphere is the one which actually has the highest moment of inertia. All right, I think I made that point clear to all of you. Fifth question. From a square plate of length L and mass M, a circular plate of mass M and radius R is removed so that the geometric center of the square coincides with that of the circle as shown in the figure. Then the shift of the moment of inertia is. Now, if you remove this and remove this, everything is symmetrical, right? So therefore, the geometrical center will still be equal to this itself. So fifth one, there is no shift in the center of mass because I have removed the circular part equally from this, and therefore there can't be any shift. It will be at the same point. So it should be 0. Okay. Two particles of mass 2 kg, 3 kg have position given by this, respectively. The center of mass has a position vector given by. A nice question here. Please look at it. The way that I'm going to obtain the center of mass will be RCM will be equal to 2 into R1 plus 3 into R2 divided by 2 plus 3. 2 plus 3. So work it out and you should get the answer. First one is 2 kg. So this turns out to be 4i cap plus 6j cap plus 8k cap, 8k cap plus 3 into the second part plus 3 into 4i cap. So 3 4s is 12i cap. Directly I'll write it. Plus 3 into 2 becomes 6j cap. Plus 3 into 3 becomes 9k cap. Divided by 5. Whole thing divided by 5. I can add up all the things which have the same components. So I caps I can add up. So this becomes 16 I cap plus 12 j cap plus 17 k cap divided by 5. So the center of mass therefore will be equal to 16 I cap plus 12 j cap plus 17 k cap by 5. So the answer is pretty simple. It has to be third one. Third one should be the answer. Very nice. Some of you have already answered that to me. So nice of you. Eighth question. A force of minus Fk acts at O, the origin of the coordinate system. They talk about the point 1, minus 1 is. Okay, I have to find out what will be the torque at that point. So torque essentially is given to be R cross F. R in this case is given to be I cap minus j cap. All right, because 1, minus 1. cross minus f k cap. Okay, this should be cross product with this. So now take the cross product. This should be minus f I cross k. We know how to do that. Minus of minus becomes plus f into j cross k. J cross k. So what will that turn out to be therefore? Minus f I cross k. I hope you all know this. I j k, if you place it like this, I j k, then I cross j will be k. J cross k will be I. Then I cross k essentially will be equal to minus j cap. So therefore this will be minus j cap plus j cross k. J cross k will be I cap. And as a result, I get this to be therefore f into I plus j. I plus j. So I plus f into I plus j. So the answer to this question therefore should be 1. Eighth one. First one.
Once again, can you explain, sir?
Sorry?
Once again, can you explain, sir?
Yeah. Torque is given by R cross F. Now, what does it say? R is given to be I minus J, because it's 1 minus 1, 1 comma minus 1, isn't it? X component is 1, Y component is minus 1. So R therefore vector is given to be I cap minus J cap. So I have to take a cross product with F. What is F given to be? Minus F k cap. So minus F k cap. I have now taken the cross product of the two. So F minus F, I took it out. I cross K, I took that. I cross K. Then minus of minus becomes plus. So I took it as plus F into J cross K. J cross K. J cross K. So I got this. Now what is I cross K? I cross K is minus J. What is J cross K is I cap. And therefore, I together get this to be, there's already one minus sign here. So it becomes F into I plus J. So that's the first option given here. First option given. All right. So I think it's now time. I will see how many more questions I have. I have, I think, few more questions. I will do this in my next class. Next class, I'll be doing gravitation. My next class is on Saturday. Okay. Marvin sir basically did I think ray optics. He'll be continuing with that. But my topic is going to be gravitation. I will do it in my next class. All right. This part also I do, plus I will also do gravitation. With this, let me say goodbye to all of you. I hope these classes are useful for all of you. I hope it is.
Sir, can you send?
That you all are coming for.
So please send the
Sir.
PDF, sir.
Can you send? What did you say?
PDF.
Sir, please show. Sir, please show me the slide of rolling on an inclined plane.
Okay. I will send the whole thing to you. Okay. Soon after this class, I'll send it. But anyway, you're asking me for it, and therefore I'm basically pulling out that part. Here it is.
So Saturday, will you do more sums on this?
Yes,
Yes.
just a minute, wait, sir.
Let's do gravitation.
Hello, sir.
Okay,
Yes,
sir.
sir.
Thank you, sir.
Sir, we didn't get PDF.
Sir, can I contact
You will
you?
get PDF now.
Excuse me, sir.
Yeah.
Sir, a tiny doubt on the previous question.
Yeah. Tell me, please. Yeah.
Sir, we actually had a point like 1 comma minus 1.
Correct.
And so could we find the angle by that?
You can. That also is another way of doing it. But your answers are all in terms of I and J. Right? If you look at
Sir,
the
please.
they're all in terms of IJ. So calculating the angle and then bringing back to this IJ would be a problem. You'll have to again struggle twice. So instead, use the cross product directly, R cross F. That becomes easy. Yeah.
Sir,
Yes, sir. Thank you, sir.
Sir, the rolling on an inclined plane slide, please. I just want to write
I
it.
showed you, no?
Your time, yeah.
Sir, I didn't know.
That's okay. That's okay.
Thank you so much, sir.
Yeah, you're welcome.
Thank you, sir.
Is it okay? Can I now move on? The student who asked me for this?
Yes, sir.
Okay. Yeah. Okay. I think now we can end.
Thank
Or
you,
should
sir.
we end or not, Prajwal?
No, I'll
Thank
lock
you,
the
sir.
meeting.
Oh, you lock, is it? Then I have
Yes,
to
sir.
transfer the this thing to you.
Yeah, host.
You should become now the host.
Yes, yes,
Yeah?
yes. Transfer it.
Where are you now in this?
Prajwal JES.
Correct, but I know your name, but I just wanted to know where you are. You switch on your video, then I think I will get.
Is it?
It's always easier that way, no?
Okay.
Make post. Bye bye.
Yeah, bye. Student, leave the session.
Sir, next class ಯಾವ್ದು sir?
ಟೈಮ್ ಟೇಬಲ್ ಇದೆಯಲ್ಲ ನೋಡಿ ಗ್ರೂಪ್ ಅಲ್ಲಿ.
ಸರಿ sir.
Student, leave the session. Student, leave the session.